Many hundreds of thousands of years ago, there was not ice where we stand now, but it accumulated over time due to the fact that it's cold here and the snow layers, one by one, storm after storm, build up to the point where the Greenland ice sheet is over 2 miles thick. Inside the ice and inside the snow are stored chemical indicators of past climates, so that from ice coring science, we know that climate can change in less than 10 years.
Yeah, ice cores are pretty remarkable because they contain annual layers. So every year that snow falls, because it doesn't melt, it just accumulates. You actually can see the annual layers just like tree rings. So we know very well what the age of the ice is. And as it piles up and piles up, it forms, if you will, a sort of a library of ancient climate. And if you core through it, drilling down pieces of ice, you can reconstruct the history of past climate, just like reading a book. Ice cores have these little bubbles of air trapped in them, and that allows us to measure the composition of the ancient atmosphere very directly and with very high confidence.
Fern is snow that is more than 1 year old. And here at the summit of Greenland, we're in a cold spot so that snow does not melt from year to year. So that it is piled up until we have about 80 meters of what we call fern, with about 60 centimeters of snow. Snow is from this year on top of it. What we're doing here is looking at the physical nature of the fern. So we're looking at how dense it is versus depth. It's going to get more dense as it goes to depth. And look at how much was deposited each year. And step back in time to see what the temperature and what the accumulation rate was many years ago.
I'm about 2 meters down and I'm shaving off this part, and then I've been shoveling out the other pit. I think I'm about close. I wanted about that far apart. It's a real bummer when you get a hole, if you get it a little too thin in spots, and then you end up with a hole in the wall. So I'm going to try to avoid that.
So Zoe's been digging a snow pit in the top 2 meters. That's the most fragile place. Deeper down, we can take ice cores and fern cores and they'll hold together. But snow pits pretty much has to be done in situ.
So up here we have the lighter summer layers. Where I'm pointing right now is a hoar layer, which is caused by a fog event condensing on the surface of the snow. So you get these very light in appearance layers that are very coarse grains and very fragile. When I push on it, the grains will fall out. And then here is an ice layer that's caused usually by the wind scouring the surface. And then below that we start getting into the winter layers, which are darker in appearance. And they're darker in appearance because they're denser. They're rounded grains that have been tightly packed in together by the wind. And so we're trying to understand how these changes at the surface affect what happens when the snow gets buried and then compressed into ice. Because you actually see these lighter layers and darker layers even into the ice itself. And it's used to date the core.
So here what we're doing is we're going to, for every run of the drill that they do, and a run is going down the hole and coming back with core. We'll bring the core over here, we'll lay it out, we'll brush off the chips, we'll measure the length of the core, and we will weigh the core so we know how much mass is there, and then we can calculate the density of that increment. Elise is the master eyeball. Madam Sharp Eyes.
101.7.
Oh,
Beautiful.
beauty. That's a keeper.
The sun's getting about as low as it's gonna get, huh? It's like 10 till midnight.
We're interested in the gases that are trapped in the bubbles, and the gases start to leak out if the temperature is warmer than minus 15 centigrade. This thing goes down in the hole. It's vertical. This little foot here sits on the very bottom of the borehole, and this part is rubber, natural rubber, still flexible even at minus 50 centigrade. But it squeezes against the side of the borehole, makes a seal, so we don't suck any atmosphere down in. And then this line right here, you see that thing? That's the intake. That's where the actual sample comes in. Don't put any weight on the tubes. The tubes are not the strength member. The weight's supposed to be on the green tape.
Yes, we're down to the wire, but we're also achieved what we wanted, have all our core, and we're going to shuttle them home tonight. We can look at climates in tree rings, we can look at climates in sediment cores, but ice cores drilled on ice sheets have a special character. That's the only way that we can learn about past atmospheric composition. There are many things that are not published from ice core records and from firn air records. They're not yet published because we don't understand the record. We don't understand how it came to be. This study aims to understand the processes that form that, so that we can unlock the clues to more records.
If we're going to build credible models of future climate, we really need to have great confidence in these past estimates of temperature. So what we're doing here is very important. We're making it so you can really take this one to the bank. We're making it very rock solid, so there's no ifs, ands, or buts about it. Right, finishing.
Woo!